Somewhere in the constellation Lyra, a slightly bigger, slightly heavier Earth 3.0 orbits a small orange sun, and the numbers say it shouldn't just be habitable, it might already be occupied. In this video, we're going to zoom in on Kepler 442b and show how James Webb and future telescopes could read its atmosphere from 1,196 light-years away and answer the question we've only ever guessed at. Is someone already living there? How close can a planet get to being Earth without actually being Earth, and still force you to take it seriously as a potential home? Kepler 442b is one of those planets. It sits in the constellation Lyra, about 1,196 light-years away. In more down-to-Earth numbers, that's roughly 11 trillion kilometers, or about 7 trillion miles. The light we see from that system left long before engines or rockets. So everything you know about this world comes from old photons and precise measurements, not from probes or pictures. Start with its size and mass, because those already tell you a lot. Kepler 442b has a radius about 1.34 times Earth's, and a mass about 2.36 times Earth's. That puts it solidly in the super-Earth category. Too big to be a twin of our planet, too small to be a gas or ice giant like Neptune. At this size and mass, the most straightforward explanation is that it's a rocky planet, with a surface made of rock and metal, not just deep atmosphere. This is important, because if you want oceans, continents, and a surface ecosystem, you need a place where solid ground and liquid water can actually exist. The gravity there would hit you harder. With that mass and radius, the surface gravity is roughly 1.3 g. If you weigh 70 kilograms here, about 155 pounds, on Kepler 442b, you'd feel like you're carrying about 90 kilograms, roughly 200 pounds. Moving would feel heavier, running would cost more energy, jumping would be disappointing. But from a habitability point of view, 1.3 g is still within a range where humans, and probably many other forms of complex life, could adapt. Next, look at where this planet orbits. Its star, Kepler 442, is cooler and dimmer than our Sun, so its habitable zone is closer in. Kepler 442b orbits at about 0.409 times the distance between Earth and the Sun, around 61 million kilometers, or 38 million miles. That is closer than Mercury orbits our Sun, but because the star is only about 12% as luminous as the Sun, the planet does not fry. When you add the lower luminosity and the shorter distance together, Kepler 442b ends up receiving about 70% of the light and energy that Earth gets. 70% of Earth's sunlight is a key number. Less light means a cooler starting point, but not necessarily a frozen planet. The balance comes down to the atmosphere. If Kepler 442b has a thin atmosphere with little greenhouse effect, the surface could be locked in ice. If it has a thicker atmosphere with more greenhouse gases like carbon dioxide and water vapor, it can trap more heat and push surface temperatures up into the liquid water range. The energy coming in is in the right zone where a realistic atmosphere can make the difference between a global snowball and a world with open oceans. Astronomers talk about the equilibrium temperature of a planet, the temperature you'd get if it were a bare, airless rock, only absorbing and re-radiating the starlight it receives. For Kepler 442b, that number comes out to roughly 233 Kelvin, which is about minus 40 degrees Celsius, also minus 40 degrees Fahrenheit. That sounds brutally cold, and in simple terms, it is, but that's before you add any greenhouse warming. Earth's own equilibrium temperature, without an atmosphere, would be below freezing too. Our atmosphere adds enough extra heat to push the average surface temperature above zero, so that liquid water can exist over large areas. Kepler 442b starts from a similar kind of deficit, just a bit colder, and lets the atmosphere decide the final outcome. Now look at time, the length of a year. Kepler 442b completes one orbit in about 112.3 Earth days. So if you lived there, you would mark off a full year in less than 4 of your current months. Climate cycles, seasonal shifts, and any biological rhythms would all be running on this shorter clock. If the planet has the tilt like Earth, you'd still get seasons, but they would be compressed. Winters and summers would be shorter and more intense, and life would have to be tuned to fast changes over a 112-day cycle instead of a 365-day one. Even with the short year, the orbit itself looks stable. Its distance from the star does not swing wildly in and out. The orbital eccentricity is estimated to be low, which means the planet does not move much closer or much farther from its star over the course of its orbit. That keeps the incoming energy relatively steady, which is good news for climate stability. You don't want a world that spends half its year roasting and the other half in deep freeze if you're hoping for long-term surface habitability. Put all of this together. You have a planet that is bigger and heavier than Earth, but still likely rocky with a surface you can stand on. It orbits a long-lived, relatively calm star at a distance where it receives about 70% of Earth's sunlight. Its raw, no-atmosphere temperature is cold but not extreme by deep space standards, in a range where a moderate atmosphere can realistically create liquid water on the surface. Its year is short, but its orbit is close to circular, which favours stable long-term conditions. This is why many researchers treat Kepler 442b as an Earth 3.0 style candidate, not just another rock. On multiple independent rankings that score exoplanets for habitability, it keeps landing near the top, because all the basic physical parameters line up unusually well for long-lasting surface water and a thick atmosphere. There is a catch hidden inside that compliment. A planet that checks this many boxes for long-term habitability also raises a harder question, because a world that can stay stable, wet and temperate for billions of years is not just habitable, it becomes a strong candidate to already be inhabited. Kepler 442b is not just a place where life could exist in theory, it is a place where, if life tends to appear on planets like this, it has had a serious amount of time to start, adapt and spread. So once you understand the basic physical setup of this planet, size, mass, distance, light, temperature and orbit, the next step is obvious and much more uncomfortable. How do you actually check from here whether this potential Earth 3.0 is just empty terrain, or whether someone else has been using it for a very long time? So how do you even spot a planet you can't see circling as a star that's just a faint dot more than 1,000 light years away? You do it the way the Kepler Space Telescope did it, by staring at more than 150,000 stars at once and watching for tiny regular dips in brightness when a planet moves across the star's face. That's what Kepler did for years, just taking brightness measurements over and over, turning the sky into a giant spreadsheet of numbers. Kepler 442 was one of those stars, and every roughly 112 days its light dropped by a tiny repeatable amount. That repeating drop is Kepler 442b, crossing in front of its star like a moving speck, blocking a small fraction of the light. This method is called transit photometry. In simple terms, you measure how bright the star is, wait until a planet passes in front, see how much dimmer it gets, then watch it brighten again. Do that multiple times with the same timing, and you know it's not random noise, it's something in orbit. For Kepler 442b, those repeated 112-day transits were confirmed and published in 2015. From that moment, this world stopped being a guess and became a confirmed planet in a catalogue. But seeing a star blink is one thing. Turning that blink into real physical numbers, like this planet is about 1.34 times Earth's radius, is another. How do you get from a tiny dip in brightness to the size of an entire world? The key is how deep that dip is. If a planet crosses a star, the amount of light it blocks depends on how big the planet is compared to the star's disk. If the star's brightness drops by, say, a fraction of a percent, that tells you the ratio of the planet's area to the star's area. You already know the star's radius pretty well from its spectrum and brightness, so you can back out the planet's radius directly. For Kepler 442b, the transit depth says its radius is about 1.34 times that of Earth. That's not a guess, that's a direct measurement from the shadow. Once you have the radius, you can combine it with what we know about how planets of different sizes tend to pack mass. Rocky planets of that size usually fall in a certain mass range, and when you plug in Kepler 442b's numbers, you get about 2.36 times Earth's mass, and a surface gravity around 1.3 g. If you weigh 70 kilograms here, about 155 pounds, on Kepler 442b, you would feel like you're carrying around 90 kilograms, roughly 200 pounds. Every step, every movement costs more. For life, that means stronger bones, thicker muscles, shorter jumps, but still a physically reasonable environment. For the data, it tells you this planet is dense and compact enough to be mostly rock and metal, not a puffed-up gas ball. Okay, so the size comes from the shadow, but how do you know that mass isn't just an assumption from statistics? How do you actually weigh a planet you've never seen, orbiting a star that's just a point of light? You use another trick called radial velocity, or the wobble method. The planet doesn't just orbit the star, both star and planet orbit a common centre of mass. That means the star itself moves slightly toward you and away from you as the planet goes around. That tiny motion leaves a fingerprint in the star's light. The spectral lines shift slightly to the blue when the star moves toward you, and slightly to the red when it moves away. For Kepler 442, that wobble is just a few meters per second, basically walking speed, around 7 to 10 miles per hour. It's a tiny signal buried inside the star's own activity and noise, but with sensitive spectrographs on large ground-based telescopes, you can pick it out. Once you measure how fast the star is wobbling and you know the orbital period from the transits, you can calculate the planet's mass. Now, mass and radius are both pinned down, not just guessed. Transit plus wobble is the tag team that takes Kepler 442b from mysterious dip to rocky super-Earth with about 1.3 g surface gravity in a 112-day orbit. But that still leaves you blind on the most important part: what is actually happening at or above the surface? Empty rock, toxic atmosphere, global ocean, or something stranger? All of those look the same if you only know size and mass. So where does James Webb enter this story, and why does it matter for a planet like this? The James Webb Space Telescope is built to work primarily in infrared light. That's the colour range where cool objects like planets and warm gases emit strongly, and where the fingerprints of many important molecules show up. When a planet like Kepler 442b transits its star, a tiny bit of the starlight filters through any atmosphere around the planet before reaching you. That light carries an imprint, a pattern of absorption lines, from whatever molecules are in the air. Webb can split that filtered starlight into a spectrum, a detailed barcode of wavelengths, and look for dips at specific infrared bands where gases like carbon dioxide, methane, water vapor, and other molecules absorb. We've already used Webb to do this for hot Jupiters, sub-Neptunes, and some potentially habitable sub-Neptune candidates like K-2-18b. In those cases, Webb has picked up clear signs of carbon dioxide, methane, and other compounds at distances of tens to hundreds of light years. That proves the method works. From our side, the planet is just a dot we can't resolve, but Webb's sensitivity lets us read the atmosphere indirectly, by tracking how the spectrum of the star changes during transit. For a truly Earth-like super-Earth, the signal is much weaker, just a few parts per million change in the total light. But in principle, the same technique applies. Here's the reality check you have to keep in mind though. As of now, Kepler 442b is still a prime target on paper, not a world Webb has already dissected. The system is faint, the star is around magnitude 15 and it's far, about 1,196 light-years away. That makes transit spectroscopy extremely demanding. You would need to observe many transits, stack all the data, and fight instrument noise and stellar noise the entire way. Webb's time is limited and heavily contested, and so far it has focused on closer, brighter targets where the signal is stronger. So the same tools that have already pulled atmospheric details from hot Jupiters and sub-Neptunes could, in theory, be turned on Kepler 442b, but it would require a long campaign, repeated observations, and a major commitment of telescope time. This is not a quick snapshot, it's a multi-year effort. That's where the tension really climbs, because the basic sequence is brutally simple. Kepler told you, something about 1.34 Earth radii is there, in the right zone, on a 112-day orbit. Radial velocity measurements told you, It weighs about 2.36 Earth masses, with gravity around 1.3 g, and it's probably rocky. Webb's job, if we ever spend the time on it, is to answer the questions that actually keep you awake at night. What's in the air? Is there liquid water at the surface, and is there any sign that life is running the chemistry on this planet, instead of geology doing everything alone? Light curves, those brightness versus time plots from Kepler, are just the first step. The real jump is from light curves to life curves, from this is a planet to this is an active world with complex chemistry, maybe even technology. You have the basic tools to try, but you haven't fully aimed them at one of the best Earth 3.0 candidates yet. So before you can even talk seriously about already occupied, you have to ask another critical question. What kind of star is powering this whole setup? How stable is it? And how much time has it actually given Kepler 442b to stay in a comfortable zone for life to start, adapt, and possibly advance? How dangerous or safe is the Sun that Kepler 442b orbits? And does it secretly make our own Sun look rushed? The star in this system is not a twin of our Sun. Kepler 442 is what astronomers call a K-type dwarf, specifically K5b. In simple terms, it's a main sequence star, burning hydrogen like the Sun does, but it's smaller and cooler. Its mass is about 0.61 times the Sun's, its radius is about 0.60 times the Sun's, and its surface temperature is around 4,400 Kelvin, compared to the Sun's roughly 5,778 Kelvin. Cooler means redder. If you could put them side by side, our Sun would look whiter and harsher. Kepler 442 would look softer and more orange. So why should you care that this Sun is smaller and redder if you're just thinking about life on a planet? Because cooler and smaller also means dimmer. Kepler 442's luminosity, the total power it puts out, is only about 12% of the Sun's. That's why the habitable zone in this system, the region where liquid water can exist on a planet's surface, is pulled inward, closer to the star. Kepler 442b orbits at about 0.409 astronomical units, roughly 61 million kilometers, about 38 million miles. That's inside Mercury's orbit by our standards, but around this dimmer star, that distance gives you roughly 70% of the light Earth gets. Lower power output might sound like a downgrade, but for long-term habitability, it's actually a big plus. Stars like this burn their fuel more slowly. K-dwarfs in this mass range can live for something like 18 to 34 billion years, about 2 to 3 times longer than our Sun's total expected lifetime. That means their habitable zones don't just exist for a few billion years and then move outward too fast. They can stay stable for tens of billions of years. You're not looking at a quick window for life, you're looking at a very long runway. That immediately raises the stakes. If a planet like Kepler 442b is sitting in the right zone around a star like this, you're not talking about a brief chance for biology, you're talking about a system that can keep conditions steady long enough for multiple rounds of evolution, maybe multiple cycles of complex life and even technology. Our own Earth has been habitable for about 4 billion years. This system could, in theory, offer 3 to 5 times that. Now there's another piece that sounds like a negative at first glance. The star's metallicity. In astronomy, metals means everything heavier than hydrogen and helium, things like carbon, oxygen, iron, silicon. Kepler 442 has only about 43% of the Sun's heavy element content. Lower metals usually mean fewer massive gas giants because you have less solid material in the early disk to build huge cores. But you can still form rocky planets if the disk is dense enough and long-lived enough. Kepler 442b itself is proof of that. It's a rocky super-Earth in a good orbit around a metal-poor star. That tells you something important. You don't need a Sun-level metal content to build complex planetary systems with terrestrial planets. In fact, some studies suggest that slightly metal-poor stars might even be better at producing multiple rocky planets without a bunch of giant planets migrating in and wrecking the inner system. So you have a smaller, cooler, longer-lived star with fewer heavy elements, but at least one very promising rocky planet. The next question is, how much time has this system actually had so far, and is that enough for life to start doing anything noticeable? The estimated age of Kepler 442 is about 2.9 billion years. That's younger than our Sun, which is roughly 4.6 billion years old and younger than Earth's current biosphere age. But compare it to how life evolved here. On Earth, it took on the order of 2 billion years to go from life exists but the atmosphere has almost no oxygen, to microbes have pumped enough oxygen into the air to change the entire planet, the Great Oxygenation Event. If Kepler 442b formed early in the life of its star and conditions were right, a 2.9 billion year timescale is already long enough for microbial life to emerge and start reshaping the atmosphere. You're not guaranteed that it happened, but you can't dismiss it as too young either. It sits in a window where no life, only simple microbe, and serious atmospheric impact from biology are all on the table. Now, you also have to ask how rough this star is on its planets. Many small cool stars, especially M-dwarfs, are notorious for flares, bursts of X-ray and ultraviolet radiation that can hammer planetary atmospheres and strip them away over time. TRAPPIST-1 and similar red dwarfs are famous for this problem. K-dwarfs like Kepler 442, though, are generally more quiet than those very small M-dwarfs. They're a kind of middle ground, cooler and longer lived than Sun-like stars, but not as violently active as many red dwarfs. Studies of Kepler 442's X-ray and far ultraviolet emissions suggest it's relatively calm. That means fewer huge flares, less high-energy radiation slamming into the top of any planetary atmosphere, and less chance of slowly eroding it away. For a planet like Kepler 442b, sitting at about 0.409 astronomical units, that matters a lot. Higher gravity on the planet's surface helps it hold onto an atmosphere, and a quieter star hits that atmosphere with fewer destructive blasts. That combination increases the odds that any air present early on has survived for billions of years, instead of being blown off into space. So pull these threads together, you've got a star that's smaller and cooler than the Sun, outputting only about 12% of the Sun's power, but doing it in a slow, steady way that can last tens of billions of years. You've got a metallicity lower than the Sun's, but still perfectly capable of building rocky planets, as Kepler 442b proves. You've got an age of about 2.9 billion years, which is already long enough for serious microbial evolution, if life ever started there. And you've got a relatively calm, high-energy environment, which helps planets keep their atmospheres and protects any surface biosphere from constant radiation disasters. That combination is exactly the profile you'd pick if you were designing a star for the long-term habitability, not just a quick burst of it. Long lifetime, moderate activity, stable habitable zone. It's the kind of setup that could host life not just for billions, but tens of billions of years, and could host civilizations that might have risen and fallen long before humans even existed. And that's where the already occupied question stops being a casual thought and starts becoming a serious scenario. If any type of star is going to host civilizations that have had huge stretches of time to build megastructures, fill their skies with satellites, or beam power across their system, K-dwarf systems like this are prime suspects. Our Sun gives us a decent run. Kepler 442 gives its planets timescales that make human history look microscopic. So now you know the star is not a problem, it's an advantage. The next question is, under that long-lived orange light, with that stable energy flow, how does a 112-day year and a slightly stronger gravity actually play out on the ground? Day to night, season to season. And does that environment push life in a different direction than the one you're used to on Earth? How different does a year feel when it lasts only 112 days and your whole sky is dominated by a small orange star sitting far closer than our Sun ever appears? Kepler 442b orbits its star at about 0.409 astronomical units, around 61 million kilometers, roughly 38 million miles. That's just a bit farther from its star than Mercury is from the Sun. Mercury sits at about 0.38 astronomical units. If you only heard planet this close to its star, you'd probably picture a baked, airless rock, but that's where the key difference kicks in. Kepler 442 is much dimmer than our Sun. only about 12% of the Sun's total power output. So even though Kepler 442b is on a tight inner orbit, the energy it receives ends up comparable to a slightly dimmed Earth, not a scorched Mercury. You're dealing with a kind of trade, closer distance but weaker star. The end result is that Kepler 442b gets about 70% of the sunlight Earth does. That's enough energy for a serious climate system, clouds, winds, maybe oceans, without forcing the planet into a runaway greenhouse like Venus. It's a high payoff spot, close in but not overheated, which matters a lot for long-term stability. Too far out and you fight permanent ice. Too close in and you risk boiling your oceans away over geologic time. Now look at the timing of the orbit. One full lap around the star takes around 112.3 Earth days. That's the length of a year on Kepler 442b. So all the orbital dynamics, all the seasonal effects, all the long-term climate cycles are running on a clock that's roughly 1/3 of our own. You would mark off 3 years there in the same time you mark off one here. That doesn't just change the calendar, it changes how any potential biosphere has to organise its life cycles. There's another major question behind that orbital period. How fast is the planet rotating and is it tidally locked? When a planet orbits close to its star, tidal forces can slow its rotation until one side always faces the star. Like the moon always shows one face to Earth. That leads to a permanent day side and a permanent night side, which complicates surface habitability. On Kepler 442b, calculations put it just outside the region where tidal locking is strongly expected for a planet of this size and distance around a star of this mass. So the most likely scenario is that Kepler 442b still spins, with a day length somewhere in the range of tens of hours to a few Earth days. That means it probably cycles through normal day-night phases, not a static half-lit, half-dark world. No eternal dayside inferno, no frozen night-side hemisphere locked in total darkness. Instead, you get a rotating planet with moving weather systems and a terminator line, the day-night boundary constantly sweeping across the surface. That rotation is crucial. A spinning planet with a decent atmosphere can move heat from the day side to the night side, smoothing out temperature extremes. Winds and jet streams can distribute energy around the globe, and cloud systems can form and break up in patterns you can actually predict. A non-locked rotation helps you build a more Earth-like climate, even if the details are different. Now add gravity to the picture. Surface gravity on Kepler 442b is around 1.3 g, about 30% stronger than Earth's. That doesn't change the orbit, but it changes what the orbit feels like on the ground. Oceans would be held a little tighter. The curvature of the sea surface would be slightly less obvious over large distances. Waves would crash down with more force. A 3-metre wave, roughly a 10-foot wave, they would hit harder than the same size wave here, because every kilogram of water weighs 30% more. Mountains would also be affected. Stronger gravity makes it harder for crustal rock to support very tall peaks before they start to slump under their own weight. That could mean fewer ultra-extreme heights like the Himalayas, and more moderate but widespread ranges. Tectonics, if the planet has it, would still build topography, but the upper limit on mountain height would likely be lower than Earth's. The result could be a surface shaped by shorter, steeper gradients and faster erosion, especially if strong gravity and dynamic weather are working together. Denser air is also likely in a higher gravity environment, assuming there's a similar amount of gas available, because the atmosphere is pulled in closer to the surface. Denser air plus stronger gravity can make storms more intense at ground level. Raindrops hit harder, winds feel heavier, and pressure differences can drive more compact, high-energy systems. You're still in a physically reasonable range for life, but the whole planet feels like it's turned the strength knob up a bit. Now go back to the 112.3-day year and ask what seasons look like. If Kepler 442b has an axial tilt like Earth's 23.5 degrees, then it will get seasons as it orbits, one hemisphere tilted more toward the star, then the other. But all of that has to play out in about 1/3 of the time we're used to. Each season would be compressed. Instead of a 3-month winter, you could be looking at something more like 4 to 6 weeks, followed by an equally short spring, a brief summer, and a quick autumn. For any potential biosphere, that means fast, coordinated responses. Migration patterns would be tighter, and plant-like organisms would have to shift growth and dormancy phases on a compressed schedule. The year is shorter, but the physics of energy input still forces certain patterns: colder periods, warmer periods, transitions. Life either adapts to that rapid pacing, or it gets pushed to regions where seasonal variation is weaker, like around the equator. The good news for climate stability is that Kepler 442b's orbit is not a wild ellipse. Estimates put its orbital eccentricity around 0.04, which is only slightly more stretched than Earth's. That means its distance from the star stays relatively steady. It doesn't dive in much closer at one part of the orbit and then swing out dramatically farther at another. The incoming energy doesn't whiplash up and down with each year. It stays within a relatively narrow range. For climate, that kind of near-circular orbit is exactly what you want. It supports long-term predictability. Ice caps, if they exist, don't have to deal with extreme melting and refreezing cycles every year. Oceans don't have to constantly absorb and shed huge swings in heat. Complex ecosystems, if they develop, can rely on reasonably consistent patterns over millions of years, instead of being smashed by recurring extreme orbital seasons. So when you line up the orbital mechanics, you get a very specific picture. Tight orbit, but around a dim star, so the energy level looks like a slightly dimmer Earth, not a burned out rock. Year length of 112.3 days, likely with a rotating planet, not tidally locked, so you get normal day-night cycles and a global circulation system. Surface gravity around 1.3 g, shaping oceans, mountains and storms, but still in a range where biology can realistically adapt. Low eccentricity around 0.04, which keeps the energy input smooth across the year and avoids extreme orbital seasons. On those parameters alone, before you even talk about interior structure or atmosphere chemistry, Kepler 442b already looks like one of the most Earth-ish exoplanets we've found. It's not a copy, but it checks the boxes that matter for climate and long-term stability. Nearly circular orbit, non-locked rotation, relatively Earth-like flux. Orbital dynamics by themselves put this world near the top of the list when you ask, where are the conditions for a stable, long-lasting surface environment most likely to exist? But orbital mechanics can't tell you what it feels like for a body to actually stand there. They don't tell you how your muscles, your lungs, your bones, and your sense densities would react when you drop onto a rocky surface under 1.3 g with that sky and that gravity pressing down. To get to that level, you have to go deeper into what's inside this planet, what its crust and mantle are doing, and what that means for the surface a human body would experience. Stepping onto Kepler 442b, the first thing that hits you isn't the sky, it's your own body, arguing with the ground under your feet. This planet pulls on you with about 1.3 g. If you're 70 kilograms here, about 155 pounds, your body feels like 91 kilograms there, around 200 pounds. Same bones, same muscles, but every move costs more. Walking feels like you're always wearing a heavy backpack, running feels like pushing through knee-deep water, and jumping becomes a short, awkward hop. That's your nervous system's first lesson about what kind of world Kepler 442b really is. The numbers that lead to that feeling come from basic physics, radius and mass. Kepler 442b is about 1.34 times Earth's radius and roughly 2.36 times Earth's mass. Combine those and you get a bulk density sitting in the rocky range, similar to or a bit higher than Earth's 5.5 grams per cubic centimetre. If the density were much lower, you'd suspect a thick hydrogen and helium envelope, a mini Neptune with no real surface. If it were much higher, you'd be thinking about an iron-heavy world with a relatively thin rocky shell. Right now, the best fit is scaled-up Earth, an iron core, a silicate mantle, and a crust, not a small gas planet. Inside, that extra mass matters. More mass means more internal pressure and more leftover heat from formation. It also means more heat from radioactive decay in the interior. All of that feeds mantle convection, the slow churning of rock over millions of years. On Earth, that convection drives plate tectonics, mobile plates, subduction zones, mountain building, volcanoes, and long-term cycling of carbon between the mantle, crust, oceans, and atmosphere. A slightly more massive world like Kepler 442b has a good chance of stronger or longer-lived convection, which boosts the odds that it has some form of plate tectonics too. Now, back at the surface, let's stay with your body for a second. Under 1.3 G, your skeleton is under constant extra load. Over evolutionary time, that pushes life in a certain direction. You'd expect shorter, stockier builds, strong bones, dense muscles, lower centres of gravity. Tall, thin structures, whether they're trees or animals, are more likely to buckle or break. Joint stress goes up. Hearts have to push blood against a steeper gravity gradient, so circulatory systems might be overbuilt compared to ours. More powerful pumps, thicker vessel walls. Flight is a special case. In higher gravity, taking off is harder, staying up is harder, and crash landings hurt more. If Kepler 442b has a reasonably dense atmosphere, that helps, because denser air generates more lift at a given speed. But even then, you'd expect flyers to be compact, with high wing loading, and to rely more on soaring and gliding on strong updrafts than on constant flapping. Think less giant, fragile gliders, more muscular, high-control flyers hugging safe air currents. Gravity also reshapes the planet's face. Mountain ranges can't climb as high before rock starts to deform and collapse under its own weight. On Earth, Everest reaches nearly 8.8 kilometres, about 29,000 feet. On Kepler 442b with 1.3 G, the maximum sustainable mountain height is lower. You get more modest peaks, but erosion works faster, because water and ice are heavier and more energetic when they move downhill. Rivers bite into rock with more force, landslides hit harder, and sediment gets carried more efficiently toward low ground. Oceans feel the difference as well. A 4-kilometre deep ocean here, about 13,000 feet, produces a certain pressure at the seafloor. On Kepler 442b, you reach that same pressure at a somewhat shallower depth because each metre of water weighs more. If the planet has large water inventories, tens or hundreds of kilometres of water in places, the pressures at depth get extreme faster. At some point, water stops behaving like familiar liquid and forms high-pressure ice phases, solid forms of water that only exist under huge pressures, locked in between the ocean above and the rocky mantle below. That creates an interesting structure: liquid ocean on top, high-pressure ice deep down, rock beneath that. The key region for life is often the boundary between water and rock, where hydrothermal vents can form. On Kepler 442b, that rock-water interface might be partly replaced by rock ice, depending on how much water there is and how the interior is structured. But if there are regions where liquid water meets hot rock, you get potential energy gradients and chemistry similar to the vent systems on Earth that many origin of life scenarios rely on. Now bring temperature into the story. The no-atmosphere baseline for Kepler 442b is around -40 degrees Celsius, -40 Fahrenheit. That's the equilibrium temperature, raw, just starlight in and heat out, no greenhouse effect. Earth's own equilibrium temperature is below freezing too, and our atmosphere adds about 33 degrees Celsius of warming, pushing the global average into the comfortable range for liquid water at the surface. If Kepler 442b has an Earth-like greenhouse effect, similar gas mix and pressure, you could add that same kind of warming and land in a range where average surface temperatures sit near or just above freezing. A bit more carbon dioxide or a denser overall atmosphere, and you can easily move the average into the 0 to 30 degrees Celsius band, 32 to 86 Fahrenheit. That's the key zone for stable oceans, rain cycles, rivers, and long-term surface habitability. Too little greenhouse. And you get a snowball planet, with maybe a few melt zones. Too much, and you risk boiling oceans and a Venus-style runaway. Kepler 442b's starting point -40 is cold, but it's close enough for a realistic atmosphere to make the difference. If you put all that together with plate tectonics, it becomes more than just a static landscape. A slightly more massive rocky planet with active tectonics and volcanism is constantly trading gases between its interior and its atmosphere. Volcanoes release carbon dioxide, water vapour, sulfur compounds. Weathering and sedimentation pull carbon back down into rocks. Over millions of years, this kind of carbon-silicate cycle acts like a thermostat. If the planet warms, weathering speeds up, pulling more CO2 out of the air. If it cools, weathering slows, volcanoes win, CO2 builds up again. On Earth, this is one of the main reasons our climate has stayed within a habitable band for billions of years, even as the sun slowly brightened. Kepler 442b, with more mass and more internal heat, could run a similar or even more robust version of that thermostat for longer. That means its surface environment isn't just habitable once, it can be pushed back toward habitable after disturbances, asteroid impacts, episodes of increased volcanism, shifts in orbital parameters. For life, that's huge. You don't need perfect stability, you just need a system that doesn't spiral into permanent snowball or permanent hothouse after every big hit. From the standpoint of occupied or not, this is where the geology stops being background and turns into a direct factor. A thick, dynamic crust, active volcanism, and potential plate tectonics mean long-lived outgassing, recycling, and energy flow. That's a planet with a full pantry of gases, minerals, and chemical gradients, and a stable power supply in the form of interior heat and steady starlight. It's the kind of setup where a biosphere, once started, can dig in and adapt through multiple environmental swings instead of being wiped out every time the climate twitches. For any technological civilization, these same traits matter too. Plate tectonics concentrates ores, volcanism brings deep materials closer to the surface, and a long-lived, regulated climate gives you time for agriculture, cities, and industry to arise and survive. A planet that is geologically dead or that flips between extremes is a hard place to build a long history. Kepler 442b on paper looks like the opposite. A world built to keep its surface active and chemically rich for far longer than Earth will get. So the physical side checks out. A rocky super-Earth with 1.3 G, plausible plate tectonics, potential oceans, and temperature ranges that an atmosphere can realistically tune into the liquid water zone. The body can handle it, evolution can work with it, geology keeps the system fueled. The next, harsher question is, what is actually sitting on top of that surface? A thin, almost airless sky, a thick natural greenhouse, a haze that hides everything, or an atmosphere that has been modified on purpose by something living there? How do you tell if Kepler 442b is just a cold rock with a thin wisp of gas, or a full heavy sky that's been running a climate system for billions of years? Start with the basic question, can this planet even hold on to an atmosphere? On Kepler 442b, gravity is about 1.3 G, roughly 30% stronger than Earth's. Gas molecules have to climb a steeper gravity well to escape. On top of that, its star is a relatively calm K-dwarf, not a hyperactive red dwarf blasting it with constant X-ray and ultraviolet flares. That combination, higher gravity and moderate radiation, is exactly what you want if you care about atmospheric survival. Ultra-hot super-Earths close to brighter, harsher stars get stripped down over time, losing lighter gases until you're left with bare lava or a very thin atmosphere. Kepler 442b is not in that extreme regime, which increases the odds that whatever air it started with, it has kept a lot of it. The next step is, what kind of atmosphere are you talking about? Primary or secondary? Early in a planet's history, right after it forms, it can capture a hydrogen-rich envelope from the gas in the protoplanetary disk. That's a primary atmosphere dominated by hydrogen and helium, more like what you see on gas giants. If Kepler 442b kept a thick primary atmosphere, it would start sliding toward the mini-Neptune category, a world with deep gas layers and high pressures before you reach any kind of solid surface. But planets don't stay frozen at their birth conditions. Volcanism and outgassing can slowly replace that original blanket with a secondary atmosphere built from gases released from the interior. That's mainly nitrogen, carbon dioxide, water vapour, plus smaller amounts of other gases. Earth did exactly that. Over time, we lost the primordial hydrogen envelope and gained a secondary atmosphere shaped by geology and later biology. For Kepler 442b, the big pivot is whether that same transition happened. If it shed most of its hydrogen and helium and settled into a nitrogen-carbon dioxide water mix, it behaves like a super-Earth. If it kept a thick hydrogen layer, the surface, if there is one, sits under crushing pressures and temperatures, and habitability looks very different. Right now, you don't know which path it took, but you know the planet sits in the mass and radius regime where both options are possible. That's why atmospheric data is the missing piece. You can't just look at size and mass and declare super-Earth forever. You need to see what's in the sky. That's where the James Webb Space Telescope stops being abstract and starts to matter. Webb has already gone after several exoplanets and pulled out solid atmospheric signatures. On worlds like K2-18b and other sub-Neptunes, Webb has seen clear fingerprints of carbon dioxide and methane, and there are even tentative hints of more exotic molecules like dimethyl sulfide, DMS, which on Earth is produced almost entirely by marine life. That particular claim is still under heavy debate, and might turn out to be a false alarm, but the important point for you is this: the instrument suite can detect complex chemistry from tens to hundreds of light years away, in atmospheres that are only a tiny fraction of the star's total signal. So if you ever do point Webb, or a next-generation telescope, at Kepler 442b, what are you actually hoping to see in the data? During a transit, some of the starlight doesn't just get blocked by the planet's disk. It skims through the thin shell of atmosphere around it before reaching us. That path might be only a few tens of kilometers thick, say 20 to 100 kilometers, roughly 10 to 60 miles. But in that slice, gas molecules absorb light at very specific wavelengths. Oxygen, ozone, methane, nitrous oxide, water vapour, carbon dioxide, each one leaves distinct fingerprints, narrow dips in the spectrum at particular colours. In precise terms, you're talking about changes spread over nanometers in wavelength, measured as tiny reductions in brightness at those points. In everyday terms, you're reading a barcode burned into the star's light by the planet's air. If Kepler 442b has significant oxygen and ozone, you'd see signatures in certain visible and near-infrared bands. If it has methane and nitrous oxide along with oxygen, and all of them at levels that don't make sense purely from volcanoes or simple chemistry, that's when people start using phrases like strong biosignature candidate. But there's an annoying complication: clouds and hazes. Webb's work on small cool stars like those in the TRAPPIST-1 system has already shown that many rocky or sub-Neptune planets have thick, high-altitude clouds or photochemical hazes that act like a curtain. Instead of getting a rich forest of absorption lines, you get a fairly flat spectrum, because the clouds block your view of the deeper atmosphere where many of the interesting gases reside. For you, that looks like a featureless, low-contrast spectrum, even if below those clouds there's a perfectly active ocean world with a complex climate. Kepler 442b could play the same game. A thick haze layer generated by ultraviolet light breaking apart molecules and reassembling them into complex particles could sit high above the main atmosphere. Transit light mainly probes that top layer, so you see the haze, not the full gas mix underneath. That means a flat spectrum doesn't automatically mean boring or dead, it can just mean we're blocked by clouds, so you're stuck with a brutal reality. Getting spectra from Kepler 442b will be hard, and even if you get them, interpreting them is harder. You'll be fighting haze, cloud thickness, and limited signal to noise all at once. But if the planet cooperates and gives you at least some clean windows through the atmosphere, there's another twist you have to consider. Not just natural atmospheres, but engineered ones. If Kepler 442b is biologically occupied, the atmosphere might already be pushed out of chemical equilibrium in a noticeable way. Lots of oxygen and methane together, seasonal swings in CO2, strange ratios of gases. If it's technologically occupied, things can get more extreme. A civilization with the industry can raise or lower CO2 levels deliberately. either through emissions or through large-scale removal. It can inject aerosols into the stratosphere to manage climate. Most importantly, it can create synthetic molecules that geology does not generate in large amounts. On Earth, chlorofluorocarbons, CFCs, and similar industrial gases are exactly that, molecules with strong absorption features in the infrared and microwave bands, with no obvious natural source at high abundance. If you ever saw a planet with clear signatures of long-lived industrial gases like that, especially in combination with a normal-looking mix of nitrogen, oxygen, and water vapour, you'd have a very hard time explaining it without invoking technology. That would be the atmospheric equivalent of seeing straight lines and right angles on a planet's surface, but encoded in the light. So when you talk about already occupied in the context of Kepler 442b, you're not just wondering if there's air, you're asking what kind of air, bare rock thin, dense natural greenhouse, life modified, or technology modified. Higher gravity and a calmer star make it easier for this world to keep an atmosphere for billions of years. Volcanism and plate tectonics, if they're active, can feed that atmosphere and stabilise climate. Biology, if present, can rewrite the gas mix in a way that is visible from light years away. Technology, if present, can leave even sharper, more obviously artificial markers. You're looking at a planet that has the physical ability to hold onto a sky, to cycle gases, and to support complex chemistry over deep time. The open question is whether that sky is just inert background, or the active product of life and maybe industry. And that leads directly into the next layer of the problem. Even if the planet's environment is stable and wet and long-lived, is it just habitable? Or is it actually running a climate that feels comfortable for liquid water and surface life over most of its surface for billions of years? You can park a planet in the habitable zone and still end up with a frozen desert or a baked rock. So where does Kepler 442b really land on that spectrum? By the numbers, Kepler 442b sits comfortably inside the conservative habitable zone of its star, not scraping the inner edge, not hanging off the outer edge. In plain terms, that means for realistic atmospheric pressures and gas mixes, Earth's liquid water is possible over at least part of the planet. When you run models for how much energy it gets, that incoming flux ends up closer to an Earth-like level than a lot of the headline habitable exoplanets you've heard about. Many of those are right on the fence, either almost too hot or almost too cold. Kepler 442b lands closer to centre field. Now, the key danger zones, the inner edge and the outer edge of the habitable zone. On the inner side, get too much starlight and you start pushing the oceans toward a runaway greenhouse. Water evaporates faster. Water vapour is a strong greenhouse gas that traps more heat, which evaporates more water, and the loop feeds itself. Venus is the classic case. Oceans probably boiled, water split by ultraviolet light, hydrogen lost to space, and you're left with a thick, hot CO2-dominated atmosphere and surface temperatures of hundreds of degrees Celsius. On the outer edge, the opposite risk kicks in. Not enough energy, too little greenhouse warming, and you lock into a snowball state, global ice cover, high reflectivity, even less energy absorbed, and you freeze solid. Kepler 442b, based on its distance and the star's output, seems to be well clear of both extremes. It doesn't get hammered with sunlight like an inner edge world, so a Venus-style runaway is less likely unless the atmosphere is extremely thick and loaded with greenhouse gases. It also isn't so far out that you need a ridiculous super dense greenhouse just to stay above freezing. That wider margin means there's more room for things to vary, cloud cover, CO2 levels, fractions, without instantly tipping the planet into steam bath or snowball modes. That's good news if you want long-lived oceans and a climate that can take a hit and recover. Now think about what those oceans might actually look like. Given its mass and radius, Kepler 442b could be several different surface types. It might be an ocean world, a deep global ocean with little or no exposed land. It could also be more like Earth, mixed continents and basins, with shallow to moderate oceans and big land masses sticking out. The same basic physical parameters can support both pictures, depending on how much water the planet formed with and how its interior evolved. On a 1.3G planet, water behaves a bit differently on the surface. Rivers run faster downhill because each kilogram of water weighs more and has more potential energy to dump. Erosion speeds up so even modest continents can grow huge, branching river systems, cutting into rock faster and delivering more sediment to the seas. Over millions of years, landscapes can be reshaped more aggressively, valley systems carved deeper, deltas built out wider, floods hit harder, storm surge carries more momentum. A small river there, a few hundred meters wide, might do the same carving work a larger river does here. If Kepler 442b is a deep ocean world with tens of kilometers of water in some regions, high pressure at depth becomes important. You start forming those high pressure ice phases we talked about, solid water under the liquid layers. That can change how heat and minerals circulate between the interior and the surface. But even then, the top few kilometers, where light can penetrate and where pressure is still manageable, can host complex ocean circulation, storms, and maybe a marine biosphere if life got started. What about the air and winds above all that? If Kepler 442b rotates faster than Earth, its Coriolis effect, the apparent force that deflects moving air because of the planet's rotation, gets stronger. Stronger Coriolis tends to break the atmosphere into more narrower jet streams. Instead of a small number of wide wind belts, you get more bands, each with its own pattern of storms and calm zones. Think of the banded look of Jupiter, but much softer, spread over a solid planet with a thinner atmosphere, not a gas giant. Those wind bands can create climate zones, strips of wetter, stormier latitudes and drier, more desert-like latitudes. Where those bands line up with continents or ocean basins, you get long-term patterns, permanent rainy belts, giant desert belts, storm tracks that hit the same regions over and over. That directly shapes where complex life can thrive, where large forests, grasslands or reef systems can establish, and where conditions stay too unstable or too dry for anything beyond hardy specialized forms. All of this sits on top of the deeper, slower climate engine, the carbonate-silicate cycle. On a rocky planet with tectonics and volcanism, carbon moves between the atmosphere, the oceans and the rocks. When the world warms, rainfall and weathering increase, pulling CO2 out of the air and locking it into minerals. That removes greenhouse gas and cools the planet back down. When the world cools, weathering slows, volcanoes keep releasing CO2 and the gas accumulates in the atmosphere, increasing greenhouse warming and pushing temperatures back up. It's a negative feedback loop, a planetary thermostat. Earth has stayed roughly habitable for about 4 billion years, even though the sun has grown brighter over that time, largely because of this kind of feedback. If Kepler 442b has similar tectonic activity and a decent supply of carbon, it could run the same style of thermostat. The big difference is timescale. Its star is a K-dwarf with a much longer lifetime, and its habitable zone will drift outward more slowly than ours. That gives the thermostat even more time to operate, and the climate more time to stay inside a range where liquid water and complex chemistry can persist. From an environmental point of view, that's almost overkill. Long-lived star, strong gravity to hold an atmosphere, likely tectonics to cycle gases, habitable zone position safely away from both catastrophic edges, potential oceans, and a rotation and wind system that can move heat around effectively. Kepler 442b doesn't just barely make the cut, it overachieves on a lot of the criteria we use for comfort zone worlds. But here's the part you can't skip. There's a huge difference between habitable and habited. A planet can tick every box for stable, wet, temperate conditions and still be empty, either because life never started, got wiped out early, or never managed to significantly modify the environment. At the same time, from a statistics point of view, each world like this you find, with long-term stable conditions, bumps the odds that at least some fraction of them do end up populated. Kepler 442b, on paper, tacks more "this could host life" factors than the overwhelming majority of exoplanets we've discovered. It's not proof of anything, but if you were going to place bets on which worlds are more likely to carry biospheres, worlds like this sit near the top. And if you take the next step, if you start thinking about not just life but technology, then the length and stability of its comfort zone becomes a problem in a different way. Because it means if anyone ever got started there, they have had a lot of time to do something with that planet. So the climate and oceans argue that this world could be very good real estate. The next question is, if you want hard evidence that it's occupied, not just potentially comfortable, what exactly would you look for in the light coming from that system? And how do you separate weird but natural from something is actively running chemistry on this planet right now? So how would you actually tell from this distance that Kepler 442b isn't just comfortable but already taken by life? The first big test is a specific chemical imbalance in the air. Free oxygen and methane together in high amounts, out of balance. Oxygen is chemically aggressive. It reacts with almost everything. Methane gets broken down quickly by ultraviolet light from the star. On a dead planet, you can have a little of each, but not a lot of both at the same time, because they destroy each other. On Earth, the only reason you see both gases present together is that something keeps refilling them. Plants and microbes constantly pump out oxygen. Microbes and other processes pump out methane, and the atmosphere never quite settles into the dead chemical state it wants. If you ever saw a spectrum of Kepler 442b that clearly showed strong oxygen features and strong methane features, both staying there over time, that would be a huge red flag. Not proof by itself, but a serious, this looks like active chemistry, probably biological. In plain language, it means the planet is breathing in a way that geology alone struggles to explain. Oxygen also creates a second marker, ozone. Ozone is just 3 oxygen atoms stuck together. It forms when ultraviolet light hits normal oxygen and makes some of it recombine into O3. Ozone has a strong absorption feature in the ultraviolet and visible range. On Earth, the ozone layer is our UV shield, blocking a large fraction of the harmful UV that would otherwise hit the surface. If you see both oxygen and ozone in a planet's spectrum, it tells you not only that oxygen is present, but that it's interacting with the star's light in a way that changes the UV environment. On Kepler 442b, detecting ozone along with oxygen would suggest that life, if present, might be doing the same kind of large-scale atmospheric engineering that photosynthetic life did here, changing the UV conditions at the surface and forcing everything else on the planet to adapt. Again, it's a pattern, not a single magic line. Oxygen plus ozone plus maybe some methane is a very strong "this air is being maintained" signal. Now, oxygen and methane are the classic pair, but they're not the only options. James Webb's possible detection of dimethyl sulfide, DMS, on K2-18b, even if it turns out to be wrong or overinterpreted, points to an important idea. Life might advertise itself with more than just the textbook gases. On Earth, DMS is mostly made by marine organisms. Nitrous oxide, N2O, is heavily tied to microbes and biological nitrogen cycles. There are sulfur compounds, weird organic molecules, and other gases that geology can produce in small amounts, but that life can produce in much larger, sustained quantities. If one day you saw something like DMS or N2O or other complex organics in Kepler 442b's atmosphere at levels that don't fit volcanic output or simple photochemistry, that would be a strong hint that some kind of metabolism is running nowhere. The key test is always the same: can you explain the gas with non-biological processes at that abundance? If you can't, and especially if multiple such gases show up together, the biological explanation jumps up the list. But gas composition is only one layer. The way the planet reflects and emits light over time can also tell you about surface conditions, especially oceans. As Kepler 442b rotates, different parts of its surface rotate into the star-facing side and back out. If there are large oceans, smooth water surfaces can produce a specular reflection, a focused glint of starlight at certain angles. That glint makes the planet look slightly brighter at those points in its orbit compared to others. From your side, that shows up as tiny changes in brightness as the planet spins and orbits, encoded in its light curve. You're looking at brightness shifts of a few parts per million. In rough terms, it's like trying to detect if a 100-watt bulb occasionally dips to 99.999 watts and then back up again, with a background of noise. It's hard, but not impossible with future instruments. A repeatable glint pattern would support the idea of large, relatively smooth liquid surfaces, which strongly hints at oceans. Then there are seasonal signals. On Earth, carbon dioxide levels in the atmosphere rise and fall by a few parts per million each year. Plants grow in one season, pulling CO2 out of the air, then decay or burn in another, releasing it back. At the same time, the overall reflectivity of continents and vegetation changes. If you could watch Earth from far away with enough precision, you'd see that our atmosphere and brightness literally breathe with the seasons. Kepler 442b has a 112-day year. If it has an axial tilt and seasons, and if it has a strong biosphere, you might see its atmosphere and reflected light do something similar just on a faster clock. Gases like CO2, methane, maybe oxygen, could rise and fall in a regular rhythm tied to the star's position and the planet's orientation. Over many of those short years, that would show up as small periodic shifts in spectral lines and total brightness. That's a fingerprint of a global biosphere responding to changing conditions, not a static dead world. All of this points to a key idea: you don't need radios or lasers to declare a planet occupied. A thick, active biosphere can leave fingerprints that are visible from 1,196 light-years away. The chemistry doesn't sit in equilibrium. The gas mix is constantly pulled away from the resting state by metabolism, photosynthesis, decay, and weather patterns driven by life. You're looking for a planet where the atmosphere looks like it's being pushed around by something continuous and global, not just rare eruptions or occasional chemical reactions. That's actually the more realistic, already occupied scenario for Kepler 442b. Not city lights flashing on the night side, not obvious megastructures blocking starlight, but forests, microbial mats, oceans, and maybe alien plankton, running the climate and the chemistry in a way you can detect but not see directly. The atmosphere becomes the display panel for everything happening on the surface and in the seas. If you find that kind of off-equilibrium chemistry there, sustained over multiple 112-day years, that would be enough to say with a straight face, this world is not just habitable, it's alive. And at that point, the next inevitable question hits hard. If biology has had time to reshape the atmosphere, and the star-planet system has been stable for billions of years, has anything there had enough time and opportunity to go beyond biology, into tools, machines, and technology? How would you actually tell if Kepler 442b isn't just alive, but home to something building machines, transmitting signals, and burning energy on a planetary scale? The first place you look is still the most old-school one, radio. Classic SETI doesn't try to pick up random noise. It looks for narrow-band radio signals, very sharp spikes in frequency that nature almost never produces by accident. Lightning, stars, and gas clouds all give you broad, messy radio emission. A transmitter built by a civilization gives you a tight line in the spectrum at a very specific frequency that turns on and off or drifts in a controlled way. If there's a civilization on Kepler 442b using radio at power levels similar to Earth's early TV and radar era, picking it up from 1,196 light-years away is hard, but not impossible, especially if they're beaming power, radar, or communication in our direction. If they're not aiming at us, you're mostly fishing for leakage, stray broadcast power that escapes into space. That's a weak signal, so you need huge radio arrays, long integration times, and smart signal processing to dig it out of the background. But if they are deliberately transmitting, maybe as a beacon or as part of some interstellar network, the power levels could be far higher than anything we use today. And then the detection problem gets much easier. A narrow, persistent spike from Kepler 442's direction that doesn't match any known natural source would jump straight to the top of every SETI project on Earth. Radio isn't the only game though. High-power lasers used for communication or propulsion are another technosignature. A civilization could drive spacecraft with laser beams, send data between planets or moons with focused optical or infrared light, or run some kind of interplanetary fiber-in-the-sky system. To us, those would show up as brief, sharp flashes or narrow spectral spikes in optical or infrared wavelengths, super bright at one colour, then gone. James Webb is not optimized as a laser detector, but future telescopes with fast detectors and wide field coverage could catch those flashes if they're happening often enough, or if someone out there is intentionally sweeping beams across the sky. Then there's the subtle but brutal check: the planetary energy budget. Any civilization using power on the scale of an entire planet has to dump the waste heat somewhere, and in practice that means mid-infrared emission. You know how much energy Kepler 442b receives from its star, in watts per square meter, based on distance and stellar brightness. You can measure how much infrared the planet sends back out into space, both from natural heating and from any extra waste heat. If there's a mismatch, if the planet glows slightly too warmly in certain mid-infrared bands compared to what you'd expect from starlight plus greenhouse effects alone, that could be a weak sign of artificial energy use. This is like checking the power bill of a world you can't visit. You're asking, does this planet radiate like a normal climate, or like a normal climate plus a lot of machines running? The signal would be tiny and you'd have to rule out other explanations first, like weird clouds or unusual atmospheric composition. But on very long timescales, a planet that constantly radiates just a bit too much structured heat, in a way that tracks a stable civilization-level power use, would stand out. A sharper atmospheric technosignature is artificial molecules. Long-lived industrial pollutants such as chlorofluorocarbons, CFCs, or similar synthetic compounds have clear spectral lines in the microwave and infrared bands. On Earth, they were used in refrigeration, propellants, and industry, and they don't have strong natural production pathways at high concentration. If you ever saw those kinds of molecules in Kepler 442b's atmosphere at significant levels, you wouldn't be looking at geology anymore, you'd be looking at chemistry that screams someone is running factories. From our side, detecting those would be like smelling exhaust from a factory on another continent, but done with light instead of air. They would show up as narrow absorption or emission features in the spectrum that don't match common natural gases. One gas by itself might be a fluke, a weird photochemical product in an unfamiliar atmosphere. A set of synthetic-looking gases, sustained over multiple observations, would be very hard to explain away. There's also the idea everyone jumps to instinctively: lights. If Kepler 442b has cities, they need illumination on the night side. In principle, ultra-high-resolution imaging in optical wavelengths could look for an unusually bright night hemisphere, with patterns of light that rotate with the planet, turning on and off as hypothetical continents move into darkness and back into daylight. You'd look for periodic changes in brightness that can't be explained by simple reflectivity or thermal emission, especially concentrated along likely coastlines or in consistent patterns. Right now, this is beyond what JWST can do, for a world 1,196 light-years away. The angular resolution and contrast requirements are brutal, but for future direct imaging missions, giant space telescopes with advanced coronagraphs or star shades, this kind of observation is a key long-term goal. If you can directly resolve the light from the planet separately from the star, you can start to ask whether the dark side is really dark or if something has lit it up. All of these technosignatures, radio spikes, laser flashes, energy budget anomalies, industrial gases, city lights, are different angles on the same core question: is someone there, using energy and technology in ways that physics can't hide completely? None of them are easy to detect at Kepler 442b's distance, but that's exactly why you'd focus on worlds like this first if you had limited telescope time. Kepler 442b isn't just some random exoplanet you picked out of a hat. It's a rocky super-Earth, in a stable, nearly circular orbit, sitting nicely inside the habitable zone of a long-lived, relatively quiet K-dwarf. Its star can stay stable for tens of billions of years. The planet likely has enough gravity to hold an atmosphere, enough mass for tectonics, and the right energy input to keep liquid water possible for absurdly long periods of time. If technological civilizations are rare and short-lived, you want to search where they've had the longest chance to appear and survive. That's not hot Jupiters. It's not scorched lava worlds hugging unstable red dwarfs. It's long-term habitable super-Earths around K-dwarfs. From a triage point of view, if you have a finite SETI budget, both in radio and in telescope hours, you'd put Kepler 442b high on the list. Long-term habitability means more time for life to start. More time for evolution means more chances for intelligence. More time for intelligence means more opportunities for someone to reach a technological phase that leaks signals or reshapes the environment in detectable ways. So the logic tightens, step by step. The planet looks physically promising. The star is a slow, steady engine. The climate zone is generous, not marginal. If anywhere has had time to raise a civilization, this kind of system has. The next question is not should we look, it's how exactly do we aim Webb and the next generation of instruments at a target this faint and this far away? And what does the actual observation plan look like if we really want to peel back its atmosphere and check for life or technology? How do you actually pull a full atmospheric report out of a single pixel that blinks every 112.3 days? Start with the most direct move, transit spectroscopy. Every time Kepler 442b passes in front of its star, it carves out a tiny silhouette. For a few hours from our perspective, starlight has to pass through a thin ring of the planet's atmosphere to reach us. On James Webb, instruments like NIRSpec and NIRISS can grab spectra during those windows. They measure the star's light with the planet in front, then without the planet, and subtract one from the other. You're looking for changes at the level of parts per million of the star's flux. That's a ridiculously small fraction, but that's the whole game. At certain wavelengths, the atmosphere absorbs a bit more light, so those wavelengths appear slightly dimmer during transit. The pattern of those dimmings tells you what gases are present. Carbon dioxide, water vapour, methane, ozone, each one cuts out light at its own set of wavelengths. Do this over multiple transits, stack the data, and you start to see a spectrum that belongs to Kepler 442b's atmosphere, not its star. Then you flip the geometry. Instead of watching when the planet passes in front of the star, you watch when it goes behind the star. That moment is called a secondary eclipse. Just before eclipse, you see star plus planet, both the star's light and the planet's own infrared glow. During eclipse, you see star alone. The difference between those two tells you how bright the planet is in infrared on its day side. If Kepler 442b has an Earth-like climate, its day-side brightness will suggest temperatures in roughly the 250 to 300 Kelvin range, around -23 to +27 degrees Celsius, about -9 to 80 degrees Fahrenheit. If the infrared output is much higher, then you're looking at a hotter, more greenhouse-driven world. If it's much lower, you might be seeing a heavily cloud-covered or colder planet. With enough precision, you can map how the planet's emission changes with wavelength, which gives clues about atmospheric composition and cloud coverage, not just bulk temperature. Now stretch the view out over the entire 112.3-day orbit. You don't just observe during transits and eclipses, you also measure how the total infrared brightness changes as different parts of the planet rotate into view and as the star-planet geometry shifts. Plot that brightness versus time, and you get a phase curve. The brightest point tells you when the hottest region is facing you. The shape of the curve tells you how efficiently the atmosphere moves heat around. If the hottest point lines up exactly with the substellar point, where the star is directly overhead, that suggests weak heat transport and strong local heating. If the hotspot is shifted east or west, it means winds are dragging heat away from the star-facing point. You can even infer rough temperature differences between longitudes, which hints at jet streams, day-night contrasts, and cloud patterns. It's not a weather forecast, but it's a first-pass climate map from 1,196 light-years away. All of this sounds neat until you hit the hard limit. Kepler 442 is faint. Its apparent magnitude is around 15. thousands of times dimmer than the faintest stars you see with your naked eye. For Webb, that means every spectrum is noisy, every transit signal is weak. You don't get a clean atmospheric readout from one event, you have to stack. Observe one transit, then another 112.3 days later, then another and another, over and over. Stacking transits is like taking a very long exposure photograph at night. Each observation adds a few more photons to the pile. The signal slowly rises above the noise. But to get a decent spectrum for a planet this faint, you're not talking about one or two transits, you're talking about many, maybe dozens. That translates into years of calendar time and a serious chunk of JWST's observing schedule. This is one reason Kepler 442b is still on the prime target wish list, not a completed case. The cost in telescope hours is huge. That's where future ground-based giants come in. The next generation of extremely large telescopes, ELTs, with mirror sizes in the 30 to 40 meter range, can add high-resolution spectroscopy from the ground. They can zoom in on individual spectral lines from the star-planet system and measure tiny Doppler shifts caused by winds in the planet's atmosphere. If one side of the planet's limb has air moving toward you, and the other has air moving away, those lines split and shift slightly. From those shifts, you can estimate wind speeds of hundreds of kilometers per hour, hundreds of miles per hour. You can see if there are strong eastward jets, day-night flow, or even signatures of storms. High-resolution spectra also help separate stellar noise from planetary signals, cross-checking what JWST sees at lower resolution. Put together, space-based and ground-based data give you a more complete picture than either one alone. And behind all of this, there's the part most people never see, the pipeline from idea to result. Observing Kepler 442b doesn't start with a dramatic image. It starts with scientists writing detailed proposals, arguing for why this one target deserves hundreds of hours of JWST time. Committees evaluate those proposals, decide which ones make the cut, and allocate slices of the telescope's schedule. Once the observations are taken, raw data isn't a pretty spectrum. It's a mess of detector counts, noise, cosmic ray hits, and instrument systematics. Teams have to calibrate the data, correct for instrument behavior, subtract out the star's variability, and extract the planet's tiny contribution. Then they run retrieval codes, complex models that take the observed spectrum and search through millions of possible atmospheric combinations to find which mixtures of gases, temperatures, and cloud properties fit the data best. The output is not a single answer, it's a set of probability distributions. Something like, there is a high chance of water vapor at these levels, a moderate chance of carbon dioxide at these levels, and a low chance of methane above this threshold. Every biosignature or technosignature claim has to be tested against those distributions, checked for alternative explanations, and stress tested with different model assumptions. So when you think about scanning Kepler 442b with Webb and its successors, you're really talking about a long, multi-step chain. First, define the observing strategy, transits, eclipses, phase curves. Second, gather data over many 112.3-day cycles. Third, process terabytes of noisy spectra. Fourth, run retrievals and test whether any apparent biosignature or technosignature holds up under scrutiny. That's where the real tension is. You're spending years, maybe decades of effort, watching a single point of light blink on a regular schedule, trying to decide if the numbers you pull out of it mean cold rock, a living ocean world, or planet with a civilization that's been there longer than our species has existed. And while you're doing that, you're also dealing with the fact that physics is not on your side, because faint, distant and noisy is exactly what you get at 1,196 light-years. So the next question is obvious. If the tools you have are pushing their limits, how much of this difficulty is just technical, and how much is hardwired by distance, faintness and stellar noise that you can't ever fully remove, no matter how good your telescope is? How do you study a planet when almost everything about the universe is set up to make it vanish into the noise, Start with brightness, because that's the first wall you hit. Kepler. 442 has an apparent magnitude around 14.9 to 15. The faintest stars you can see from a dark sight with your naked eye sit around magnitude 6. Each 5 steps in magnitude is a factor of 100 in brightness, so the jump from 6 to 16 is about 10,000 times fainter. At magnitude 15, you're already a few thousand times dimmer than the edge of human vision. For a photon-hungry infrared telescope like JWST, that's a serious handicap because every spectrum, every transit curve is built from photons that are arriving slowly, irregularly, and with a lot of statistical noise. That faintness hits you twice. First, you don't get many photons from the star. Second, you get even fewer from the planet because the planet is already a tiny fraction of the star's light. When Kepler 442b passes in front of the star, the fractional dip in brightness is small. When its atmosphere absorbs light at certain wavelengths, those absorption features are even smaller. You're subtracting small numbers from small numbers and trying to keep track of the difference to a few parts per million. Any detector instability, any tiny drift in the instrument starts to matter. Then there's the distance, 1,196 light years. Light intensity drops with the square of distance. Double the distance, quarter the brightness. Multiply the distance by 10, the brightness falls by a factor of 100. Kepler 442b is not one of the nearby systems you can reach with parallax-style ease. It's more than 1,000 light years out, so every bit of light that left that system has spread over an enormous sphere by the time it hits your telescopes. A spectral line that would be clear and obvious at 10 light years becomes stretched, blurred and buried at over 1,000. From a data point of view, you're trying to identify small wiggles in a spectrum that is itself faint and noisy. The signal from the planet's atmosphere is not just a whisper, it's a whisper on top of a constant roar from the star, detector noise, zodiacal light, and the telescope's own thermal background. You're stacking observations, cleaning the data with sophisticated corrections, and one wrong assumption about the noise can make a feature appear or vanish. On top of that, the star is not a perfect, stable light bulb. Kepler 442 is a small, cool K-dwarf, and stars like that have surface structure, star spots, cooler dark regions, faculae, brighter patches, and granulation patterns from convection cells boiling at the surface. All of those introduce their own spectral shifts and brightness variations. Studies show that for small, cool stars, those stellar effects can masquerade as planetary signals, especially in the near-infrared where Webb operates. If you mismodel the star, you misinterpret the planet. A patch of star spots rotating in and out of view can look like a change in the planet's transit depth at certain wavelengths. Bright faculae can distort the apparent depth of absorption features. Uncorrected stellar activity can make you think you're seeing methane or water in the planet's air when you're really seeing the star's surface behaviour. So before you even start asking what's in Kepler 442b's atmosphere, you have to nail down what kind of spectral noise is the star itself throwing at me. Then you hit the cloud problem. Even if you perfectly subtract the star, even if the photons cooperate, clouds and hazes on the planet can flatten everything. A high-altitude cloud deck, or a thick photochemical haze, can block your view of the deeper atmosphere. At JWST's resolution, a cloudy, life-rich world with strong greenhouse gases and a cloudy, barren world with mostly inert gas can both produce a nearly flat transmission spectrum because the clouds are doing most of the absorbing and scattering. That's what people mean by cloud degeneracy. Different atmospheric compositions with different implications for habitability and life can produce similar-looking data if the upper atmosphere is opaque. The spectrum tells you cloudy long before it tells you occupied or empty. You can try to break that degeneracy with secondary eclipse measurements, emissions spectra and phase curves, but each of those has its own noise and model assumptions. In many cases, you end up with broad ranges, not sharp answers. Now layer onto all of this the most human limitation, time on target. JWST is not just an exoplanet observatory, it's also looking at the early universe, the first galaxies, star-forming regions, black holes, solar system objects, and more. Every hour pointed at Kepler 442b is an hour not pointed at something else with its own angry team of scientists pushing for data. To get a solid atmospheric spectrum from a magnitude 15 star, you're talking about many transits spread over years. That's not a quick program, that's a major mission commitment. So prime target on a habitability ranking does not automatically become prime target on the actual observing schedule. Committees have to decide whether a long, expensive campaign on a faint, distant super-Earth is worth more than a survey of many closer, brighter planets, where each observation is easier. Some proposals lose simply because the math says we can learn more faster by looking at nearer systems first. With all of that pushing against you, it's fair to ask why anyone bothers arguing for difficult planets like Kepler 442b at all. The reason is simple and uncomfortable. The payoff is huge. One robust detection of a biosignature on a planet like this, oxygen and methane out of balance, or some exotic life-linked gas at impossible abundance would change the "are we alone" question from philosophy to measurement. One solid technosignature, an artificial gas or an energy budget that only technology can explain, would tell you that not only is life common, but advanced life has appeared at least twice in our galaxy. That's not a small update. That's a complete rewrite of our place in the universe. And the argument is that if you're going to sink that kind of effort anywhere, you should sink it into worlds around long-lived, stable stars in the right part of the habitable zone, with physical properties that make surface habitability plausible. Kepler 442b is exactly that kind of world, even if the photons are scarce and the noise is ugly. So you're stuck in this tension. The easiest planets to observe are not the most Earth-like, and the most Earth-like candidates are often the hardest to study. That leads to a hard question you can't dodge. If Kepler 442b is such a pain, is it really better than closer, brighter systems like TRAPPIST-1 or K2-18b? And how does it stack up when you compare all these habitable planets side by side? How do you know Kepler 442b is special when so many other habitable or interesting planets are already on the menu? Start with the TRAPPIST-1 system, because that's the one you hear about constantly. TRAPPIST-1 is an ultra-Coulomb dwarf with 7 known planets, several of them in or near its habitable zone. JWST is already looking at them. On paper that sounds amazing, a compact system with multiple Earth-sized worlds. But zoom in on the physics. Those planets sit extremely close to their star, much closer than Mercury orbits our Sun. That almost guarantees tidal locking. One side always facing the star, one side always in darkness. On top of that, many red dwarfs are flare-happy, throwing powerful X-ray and ultraviolet bursts that can strip atmospheres and hammer any surface life. So TRAPPIST-1 is a great lab for testing models, but it's a messy environment for life. Kepler 442b doesn't have those particular problems. It orbits a calmer K-dwarf, not an ultra-cool M-dwarf, at about 0.409 astronomical units, around 61 million kilometers, roughly 38 million miles. That distance, combined with the star's stability, reduces flare damage and makes tidal locking less likely. You're trading multiple close-in planets but harsh star for one really good planet around a long-lived, relatively quiet star. If you're thinking about long-term habitability, that trade looks smart. Next, look at K2-18b, the poster child for Hayean worlds. K2-18b is a sub-Neptune about 124 light-years away. JWST data suggests it might have a deep global ocean under a hydrogen-rich atmosphere, with clear signs of water vapour and tentative hints of dimethyl sulfide, DMS, in its air. If the DMS detection holds up, that's huge, because on Earth DMS is mostly produced by life. But from a structure point of view, K2-18b is not Earth-like. Its thick hydrogen envelope means high pressures and potentially very different chemistry at the ocean-air boundary. So K2-18b is exciting, but it's not Earth 2.0. It's in a completely different category, a possible ocean world wrapped in a mini Neptune shell. Kepler 442b, with its mass and radius in the rocky super-Earth range, sits much closer to scaled-up Earth than small Neptune. If you want to understand how life behaves on planets with solid surfaces, continents, and 1.3 G, Kepler 442b is the better analogue. Then you have the extreme cases like TOI 561b, the lava worlds. JWST and other instruments have started to find evidence of atmospheres around ultra-hot rocky planets that orbit extremely close to their stars, with dayside temperatures around 1,700 degrees Celsius, about 3,100 degrees Fahrenheit. These are wet lava balls, molten surfaces, rock vapor in the air. That sounds completely irrelevant to habitability, but it actually matters for Kepler 442b because it proves something important, even hellish. Close-in rocky planets can hold on to atmospheres. If a world like TOI 561b, under brutal conditions, can keep an atmosphere, then a milder, farther out super-Earth like Kepler 442b absolutely can. The survival of air on lava planets strengthens the argument that if Kepler 442b ever had an atmosphere, there's a very good chance it still does, especially given its higher gravity and calmer radiation environment. On the other end, you've got gas giants like JWST 18b. JWST has already made a kind of 3D map of its atmosphere, tracking hotspots, temperature gradients, and even regions where water molecules are broken apart on the day side. That level of detail, seeing how temperature changes with height and longitude, is possible because WSP 18b is huge, bright in infrared, and very close to its star. Secondary eclipses and phase curves are strong, easy to measure. Kepler 442b doesn't give you that kind of signal today, it's too small and too faint. But the techniques built on systems like WASP 18b are the same ones you would eventually use on a rocky world. Once you have a big enough telescope and enough integration time, eclipse mapping, phase curves, thermal emission spectra, all of that comes from gas giants first because they're easy, then later gets pushed down into the super-Earth regime. So right now, WASP 18b is practice. Kepler 442b is the kind of target you want to graduate to. Put all these together. TRAPPIST-1 giving you tightly packed flare-exposed planets, K218b giving you a possible deep ocean under a thick hydrogen atmosphere, TOI 561b and similar lava worlds proving atmospheres can survive in extreme conditions, WASP 18b showing you how to map atmospheres in 3D. They're all teaching you specific pieces of exoplanet physics, but very few of them thread the narrow path you actually care about for another Earth-ish size rocky in the habitable zone, around a long-lived, relatively quiet star, probably not tidally locked, with realistic chances of holding a stable temperate atmosphere. Kepler 442b hits more of those marks at once than almost anything else we've found. That's why habitability rankings keep pushing it near the top. It doesn't just sit in the habitable zone, it has the right kind of star, the right kind of orbit, the right mass and radius, and a host star lifetime that dwarfs our own suns. It's a good environment now, and it stays a good environment for far longer than Earth will. So when you think about a hierarchy of targets, it looks something like this. Hot Jupiters and warm Neptunes came first because they're bright and easy, and that they taught us how to read spectra. Lava worlds show us what atmospheres do under extreme heat, and how long they can last. Hycean candidates like K218b push our understanding of ocean planets and thick envelopes. But the place where the life lottery really gets serious is with Earth 3.0 worlds. Rocky super-Earths into stable orbits around long-lived stars, where climate, oceans and atmospheres can sit in the comfort zone for billions of years. That's why even though Kepler 442b is faint and far and annoying to study, it keeps coming back into the conversation. It's the kind of planet where, if you don't find life on a decent fraction of these, you have to start asking hard questions about how often life actually appears, even when the environment looks almost ideal for a very long time. And that sets up the next step in the story, because if you give a planet this much time, under this calm a star with this much potential for stable oceans and climate, the real issue isn't just could life exist, it's how far along could life have gotten by now, and what would evolution look like under higher gravity and a longer, quieter stellar lifetime. How far could life really have gotten on a world like Kepler 442b with its clock ticking on a completely different schedule than Earth's? The starting point is the age. Kepler 442 is estimated to be around 2.9 billion years old. If Kepler 442b formed early with its star, that means the planet has had on the order of 2.9 billion years under stable conditions. On Earth, the gap between formation and the Great Oxygenation Event, when microbes dumped enough oxygen into the atmosphere to permanently change it, is roughly in the same ballpark, about 2 billion years from early life to big atmospheric impact. So Kepler 442b has already had Earth from zero to major microbial takeover time available. That doesn't prove life started there, but it demolishes the idea that it's too young for anything interesting. Microbial ecosystems, large-scale biochemistry, even early multicellular life all fit comfortably inside that timescale if the planet ever became wet and stable. The real shock comes from flipping the timeline forward instead of backward. Earth is running on a tighter schedule. As the sun brightens over time, our climate system will get pushed toward a moist greenhouse state. Depending on the models, Earth may have only about 1 to 2 billion years of comfortable surface habitability left before temperatures climb high enough that oceans start to seriously evaporate and life gets squeezed toward the poles and underground. Kepler 442's K-dwarf star, by contrast, can stay in a stable main sequence phase for tens of billions of years. It has already given Kepler 442b a couple of billion years to work with, and it can keep the habitable zone in the right place for 20 billion years or more into the future. That is an insane evolutionary runway. You're talking about a world that could stay in a broadly good climate range for 10 or more times longer than Earth will. If complex life can ever arise there, it doesn't just get one shot, it gets multiple shots. Civilizations could rise and fall, ecosystems could reset and re-evolve, and the planet would still have time left on the clock. Earth's entire history from first microbes to humans is about 4 billion years. Kepler 442b could, in principle, support that entire story many times over. Now fold higher gravity into that picture, because evolution doesn't happen in a vacuum. On Kepler 442b, the surface gravity is around 1.3 g. That extra 30% of pull changes what kinds of bodies and structures are efficient. Tall, spindly organisms are more likely to break or collapse. Skeletons and support tissues have to work harder. Over millions of years, natural selection would likely favour shorter, sturdier builds. Think squat, compact frames, low centres of mass, dense musculature. Trees, if they exist, might not reach Earth's sequoia or redwood heights. Vegetation could be biased toward thick, ground-hugging forms, interlocking canopies, and strong root system to resist heavier loads and more energetic weather. Flight gets hit even harder. To take off in 1.3 g, you need more lift for the same mass. If the atmosphere is denser than Earth's, that helps, but there's still a trade. Flight might be rarer, more specialised or restricted to smaller body sizes and very efficient wing shapes. Gliding could be more common than powered flight, with organisms using strong updrafts and terrain features to save energy. Swimming and crawling, by contrast, are more forgiving. Water supports weight, and close contact with the ground lets muscles work more efficiently under higher gravity. That pushes evolution toward ecosystems where the bulk of biomass is in oceans, rivers, low vegetation and ground-based life, not huge tall forests or big soaring flyers. None of this requires wild fantasy. You don't need to invent dragons and impossible creatures to make Kepler 442b compelling. Just stick to basic physics. You have a planet with enough mass to keep internal heat flowing for a long time, likely tectonics to recycle materials, enough gravity to hold a thick atmosphere, a radiation environment that's calmer than many red dwarf systems, and a position in the habitable zone that leaves room for both observatories. and long-term climate stability. If life emerges easily on worlds with liquid water and energy, this is exactly the kind of place where it should have a decent shot. The real uncertainty is not could life survive, it's how hard is it for life to start at all? That's still an open question. Maybe life sparks almost every time conditions are right. Maybe it's rare and fragile. But if you assume even a modest probability, a few % per suitable planet, then a world that sits in the habitable zone for tens of billions of years, with active geology and a decent star, becomes a high-priority test case. Kepler 442b is an environment where you would expect multiple evolutionary experiments over cosmic time, not just a single roll of the dice. Now bring in civilizations and the time window problem, because that's where things get really uncomfortable. Technological civilizations might be rare. They might also be short-lived compared to the age of their planets, lasting tens of thousands or maybe a few million years, which is nothing on billion-year scales. If you randomly check a planet, the odds of catching a civilization right now might be low, but those odds change when the planet stays habitable for a very long time. On a world like Kepler 442b, with potential habitability lasting 20+ billion years, even a small chance per billion years of producing a technological phase adds up. Each era is a separate opportunity for intelligence and technology to appear, leave a mark, and either crash or stabilize. From our perspective, sitting in the 21st century on Earth, we care about overlap. We want their high-tech window and our high-tech window to be happening at the same time. Long-lived stars and long-lived habitable zones make that overlap more likely. That's one of the big reasons technosignature searches focus so heavily on K-dwarfs and similar stars. They simply give civilizations more time to exist and line up with us. And you have to remember, occupied doesn't have to mean currently broadcasting in our direction. A planet can be biologically occupied, full of life, even teeming with complex ecosystems, and never develop technology that leaks into space. Or it can develop technology, use it for a while, and then stop either because the civilization collapses, changes, or decides to stay quiet. In those cases, the only traces left might be in the geology and the atmosphere. Unusual isotope ratios, strange mineral deposits, artificial molecules that linger, or a biosphere that carries scars from past industrial phases. From 1,196 light-years away, you might never know if a civilization is still there building things, or if you're just seeing the leftover chemical fingerprints of a peak that happened millions or billions of years ago. You're not watching their news feed, you're looking at the integrated, time-averaged response of the planet to everything that ever lived on it. That's what makes Kepler 442b so unsettling. It's not just a potential home, it's a world that has had enough time for entire alien histories to play out, for long-lived biospheres to rise, for civilizations to appear, vanish, and leave only subtle signatures in the air and rock. So once you accept that the timeline absolutely allows for life, and even for multiple rounds of complex life and technology, you're forced into the final set of questions. What happens to us right now if Webb or a future telescope actually flags Kepler 442b as alive, or even worse, once clearly technological? How does that change our numbers, our equations, and the way we think about our own future? How does the game change if one day the data stops being interesting noise and starts being, this planet is definitely alive? Right now, everything you say about life beyond Earth is based on priors, guesses, and analogies. You know life appeared early on Earth, you know it survived huge impacts and climate swings, but you don't know whether that story is typical or a freak accident. For a planet like Kepler 442b, you're stacking probabilities, not certainties. You say good star, good orbit, good temperature range, long timeline, and you assign it some rough chance of being inhabited. That's all soft. One robust biosignature detection would smash that fuzziness. If a future Webb dataset or a next-gen telescope pulled out a clear, repeatable pattern on Kepler 442b, something like strong oxygen plus methane, or oxygen plus a secondary life-linked gas at levels geology can't explain, your view jumps from maybe life happens sometimes to life happens under these conditions at least twice that we know of. Statistically, that's a massive update. The odds that Earth is some weird one-off drop sharply. The odds that habitable zone planets around calm stars tend to spawn life go way up. That immediately feeds into the Drake equation, whether you like that framework or not. The fraction of habitable planets that actually develop life, that term FL, stops being a free-floating guess. A living Kepler 442b would give you at least one data point outside the solar system. If its biosignatures are strong and planet-wide, you'd also be indirectly touching the product of fraction that develop intelligent life and fraction that develop detectable signatures, because complex, globally dominant biospheres are more likely to eventually produce something clever. Your back-of-the-envelope estimates of how many civilizations are in the galaxy stop being pure speculation. You'd still have big error bars, but you'd no longer be plugging in arbitrary numbers just to see what happens. You'd know that habitable, long-lived super-Earths can, at minimum, support major biospheres. The question how many Earth-like worlds are alive right now would shift from any at all to how many per 100 or per 1,000. Then you hit the human side, which is messy and fast. The day a result like that drops, the conversation on Earth changes. You would be looking at a world 1,196 light-years away and saying with scientific confidence, life has taken root there. Not maybe, not possibly, but this atmosphere is out of equilibrium in a way that life explains best. That statement lands on everything at once. Philosophies that frame humanity as the central story, even everyday assumptions about our place in the universe. Older worldviews had to digest Earth is not the centre of the universe. Then the sun is just one star. Then the galaxy is one of billions. This would be the next step. Life is not unique to Earth. Any system of thought that assumed we were alone would have to patch itself quickly. And then there's policy, which right now feels hypothetical but would become very practical, very fast. If you know Kepler 442b is inhabited, even if it's just microbes or forests, do you treat that world differently? Do you point powerful radio transmitters at it on purpose, sending targeted messages, hoping someone there can pick them up? Do you start aiming high-power radar in its direction, or building optical beacons, knowing that any sufficiently advanced civilization on their side could detect that change in the noise? Or do you decide the opposite, that silence is safer? Some researchers already argue against messaging to extraterrestrial intelligence, METI, because you don't know who's listening. A confirmed living Kepler 442b would take that debate out of the abstract. You'd have a specific, clearly inhabited world on the sky map, and you'd have to decide whether to shout toward it or whisper and just listen. Even though you can't send a probe there with current technology, your electromagnetic footprint reaches them at the speed of light. In 1,000 years, the radio bubble around Earth will be 1,000 light-years wide. Kepler 442 is inside that sphere. On the technical side, a solid biosignature on Kepler 442b would act like a funding cheat code. Space agencies and governments respond to big, clear discoveries. Once you know one Earth 3.0 candidate is alive, the argument for building dedicated direct imaging missions becomes much stronger. That means huge space telescopes with chronographs that can block out starlight, or separate star shades flying tens of thousands of kilometers away to cast artificial eclipses, so you can see the planet directly. Those missions wouldn't just grab one spectrum. They'd go after color maps, multiple wavelengths, time series. You'd get pale blue dot-style views for Kepler 442 and its neighbours, watching cloud systems move, polar caps grow and shrink, maybe even picking up surface features in coarse resolution. Hycean worlds, TRAPPIST-1 analogues, other K-dwarf systems, all of them would suddenly look like higher priority once you know the template works. You'd also see a shift in the questions people ask. Right now, the main one is there life anywhere else at all? After a Kepler 442b detection, that question becomes too small. The next questions are, how many types of life-bearing planets are there? How different are their biospheres? And is life there purely microbial, or has it gone further? If technosignatures show up, it goes even further into how long do civilizations last, and what do they do with their planets over billions of years? For viewers of this hypothetical video, the emotional point is blunt. You were born into a universe where the only confirmed life was on Earth. All your stories, all your worries, all your future planning existed inside that assumption. You could die in a universe where that's no longer true, where Earth and Kepler 442b are both living worlds, is in textbooks, where school diagrams show two biospheres side by side, one local, one in Lyra. That jump is bigger than Earth orbits the Sun. It hits deeper, because it touches identity, meaning and future risk all at once. If life is common on planets like Kepler 442b, the galaxy is a very different place than if it isn't. And the only way to find out which is real is to push the hardware, burn the telescope time, and accept the brutal difficulty of pulling answers out of a faint signal over 1,000 light-years away. Once you accept that, there's one final turn in the story that matters, because all of this, the telescopes, the statistics, the ethics, is happening now, in your era. You're alive at the moment when this question has finally become testable, and that changes what looking up at the sky actually means for you. How strange is it that you're living at the exact moment in history when this question stops being philosophy and starts being an engineering problem? For almost all of human time, your species was huddled around cave fires and simple shelters, looking up at the sky with zero way to test anything. In just a few tens of thousands of years, less than 0.001% of Earth's 4.5 billion year history, you've gone from stone tools and oral stories to infrared space telescopes measuring the temperature of rocks orbiting other stars in Kelvin and degrees Celsius. You are the first generation that can seriously say, we might be able to tell if a planet 1,196 light-years away is alive. And here's the key part. When you say Kepler 442b is about 61 million kilometers from its star, roughly 38 million miles, sitting at 0.409 astronomical units, you're not guessing. When you call it about 1.34 times Earth's radius, you're not rounding a vibe. Those are hard-won numbers pulled out of tiny dips in starlight and equally tiny Doppler shifts, measured to meters per second and parts per million of flux. So where does James Webb actually fit in that timeline if you zoom out? JWST is not the final answer machine for Kepler 442b, it's the first serious draft of a much bigger story. Right now, Webb is mapping gas giants, hot Jupiters, lava worlds like TOI 561b, and weird candidates like K218b that might host deep oceans under hydrogen-rich skies. It's proving the techniques, transit spectroscopy, secondary eclipses, phase curves, atmospheric retrievals. For Kepler 442b, Webb is the pathfinder. It may never get enough time on target to give you a perfect spectrum, but it shows you where the bottlenecks are, noise levels, stellar contamination, how clouds flatten signals, how far you can stretch the current hardware. The telescopes that follow, bigger mirrors, better coronagraphs, dedicated exo-Earth missions, will use those lessons to go after Earth 3.0 worlds properly, including this one. Why does Kepler 442b keep showing up as the example in all of this when you could pick any catalogue number? Because it sits right at the intersection of hard data and heavy implications. Radius, about 1.34 Earths, mass, about 2.36 Earths, gravity, around 1.3 g, orbit, 0.409 astronomical units, period 112.3 days, distance, 1,196 light-years in Lyra, stellar type, K-dwarf, about 12% of the Sun's luminosity, age roughly 2.9 billion years. None of that is hand-waving. Those are actual measured or tightly constrained values. Every speculative leap you make, maybe it has oceans, maybe it has continents, maybe there are forests, maybe there are cities, has to stay chained to those numbers. The planet can't have the skyscraper tall, ultra-thin trees in 1.3 g without serious structural tricks. It can't be a gas giant with those mass and radius values. It can't be an inner-edge Venus clone with that insulation and that star. Unless the atmosphere is extreme, physics walls off whole categories of nonsense and leaves you with a narrower, sharper set of possibilities. That's what makes it such a clean anchor for a story like this. It's not pure fantasy, and it's not just a dry data table. It's a real world with real constraints plus a huge unknown on top. And this is the real point. You're not just looking for another Earth like you're shopping for a spare apartment. You're not hunting duplicates so you can say, nice, there's a copy of home. The question is more brutal. Does the universe routinely make occupied worlds? Or are planets like Kepler 442b mostly empty real estate? Kepler 442b is one of your best test cases because on paper it looks almost unfairly good. Long-lived star, stable orbit, solid surface, likely a ability to hold an atmosphere, energy input in the right range, enough time already passed for life to get going, and an absurd amount of time left for evolution to keep going. If you sample a bunch of planets like this and they all come up dead, that's a dark answer. It hints that life is hard to start or easy to kill, even when the environment looks friendly for billions of years. But if even one of these worlds, especially one this clean in terms of habitability, turns out to be alive, that's a universe-level update. It means that when you give physics a rocky planet in the habitable zone of a calm star and let it run for a few billion years, life is not a rare outcome, it's a common one. And if life is common in setups like this, you have to seriously entertain the idea that the galaxy is dotted with biospheres, some ahead of you, some behind you, some already gone. So the right way to end this isn't with a call to action, it's with a call to pay attention. Every 112.3 days out in Lyra Kepler, 442b completes another lap around its small orange sun. Each orbit, from your point of view, is a tiny, predictable dip in starlight in an old Kepler light curve and a line in a database. Slightly bigger than Earth, slightly heavier, slightly dimmer sunlight, slightly higher gravity. Right now, that's all it is to you. Parameters. But parameters describe real places. Those numbers either map onto a silent, sterile rock with a thick, dead atmosphere, or they describe a world with clouds, oceans, chemistry, and maybe a biosphere that has been running longer than your entire species has existed. In your lifetime, or your children's, the tools you've already launched, and the bigger ones coming after, might be enough to decide which of those is true. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.